All right, Chapter 1 review. If we have this inequality and we want to write it in set builder notation, we write it like this. It always has x with a vertical line, and then we just copy what's given. And we have to say what set of numbers x is in. So here we're not skipping any numbers, so we'll say all real numbers. If we only had 11, 12, 13, then we'd say integers or natural numbers here. Interval notation. Let's look at a number line. This is not interval notation. This is interval notation, but the number line helps you see what numbers on the left and on the right. We're going to start at 10 and go to infinity, so we can see that. Okay, do the same thing for this problem. Pause the video and try this. For set builder notation, we say x such that x is less than or equal to 5, and x is a real number. Interval notation. Let's look at the number line. We're starting at 5, and we're going to the left of 5. So that means we're going to start at negative infinity and go to 5. But now we have a bracket because we are including 5. Test for symmetry. Now we just change the sign of variables and see if we can get back to the original. So let's say that it's y equals x squared plus 4. The x-axis symmetry occurs when you can change the sign of the y. So let's change the sign of the y and see if this can be made to look like that. And it can't, because if I divide by -1, these will become negative, so it's not the same as that. So it doesn't have x-axis symmetry. Let's check the y-axis symmetry, and we have to change the sign of the x. And now we can make it look like the original, so that means it does have y-axis symmetry. And symmetry to the origin is when you change both of them and see if it looks like the original. Well, that doesn't look like the original, so it doesn't have symmetry to the origin. And then we are dealing with a function, so if you have y-axis symmetry, you can call it an even function. And if it had symmetry to the origin, you'd call it an odd function. All right, test for symmetry with this function. Pause the video and try this one. X-axis symmetry, you change the sign of the y, and that doesn't look like the original. Y-axis symmetry, you change the sign of the x. So make that a negative, make that a negative, and when you cube the negative, it's still negative. So we have no x-axis symmetry. We have no y-axis symmetry because this doesn't look like that. And now we check the origin. Let's change all the signs to a negative, 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 and now we check. Can we make this look like that? And we can just by multiplying by -1. So we say that it has symmetry to the origin, and we'd say it's an odd function. Evaluating a piecewise function. And we want to find f of -2, f of -1, f of 0, f of 4, f of 5. We need to know which of the pieces we're going to use to evaluate each of these. So if we put them on a number line, that can help us organize it. -1 and 4. This is dividing up the number line. We have to the left of -1, between -1 and 4, and to the right of -4. So we know that we're going to use this on the left, we're going to use this in the middle, and that on the right. So let's check -2. -2 is here, so we'll use this one. 2 times -2 minus 1, -4 minus 1. All right, -1. Well, that's on a boundary, so we have to check where is -1. Is it in the left or the middle? Here we have an equal sign, so we're going to use this one. X squared, -1 squared is 1. Pause the video and try the last 3 x values. 0 is between -1 and 4, so we use x squared. 4 is on a boundary, so we check, and it's included in this one. And 5 is greater than 4, so we will use -x. So 1, 1, let's go to 2, 3, 3, 2, and 4, 4. Open circle there. Let's just connect those with a max, a min. And we need to talk about the intervals of increase, decrease, relative maximum, relative minimum, domain, and range. Increase. Where is the function increasing? It's increasing from left to right on that interval, increasing here and increasing there. So it's increasing from 1 to 2, and our book just uses parentheses for every interval of increase or decrease, but you could also put brackets on that. And it's also increasing from 3 to 4. It's decreasing from 2 to 3. The relative maximum is here. We're not going to call that a maximum. It's not a relative maximum. Relative maximum has this shape. It's at 2, 3. So remember, that's an interval, and that's a point. This has an x and a y, and this has an x and an x. These are all x values. A point has an x and a y. The relative minimum is at 3, 2. That's a point. And the domain is all the x values. So it starts at 1 and goes to 4. We're going to include 1 but not include 4 because there's a closed circle there and an open circle there. And here we're going to go 1 to 4 also. The range is all of these values, the range, and there's the domain. Domain and range. So we're going to check continuity at 2. We make a table, or the table's given to us, and we look at the y values. What's happening at 2? So here we say at 2 it's undefined. We know the function is not continuous, but we also have to think about, to identify the type of discontinuity. We know this is going to 4. These are going to 4. So the function is undefined, but the limit exists. So we have these 3 steps. F of 2 exists. No. F of 2 does not exist. Limit as x goes to 2 of f exists. Yes, the limit is 4. And then our third check, or our third question is, f of 2 is equal to the limit of f as x goes to 2. And that's going to be a no because f doesn't exist. So anytime we get one of these being a no, we know it's not continuous. But when we get a graph like this where we're just missing a point and a limit exists, the graph is doing something like that. So at 2, the limit is 4, but it's missing a point. So that's a removable discontinuity. Try another one. Okay, do the three steps and see if it's continuous and what kind of discontinuity there might be. Pause the video and try that. F of 2, does that exist? Yes, f of 2 is 5. Let's do the limit of f as x goes to 2 exists. 5. This is going to 5. This is going to 4. So because these are different numbers, the limit does not exist at 2. So our final check is, does f of 2 equal the limit of f as x goes to 2? And that's a no, just because the limit doesn't exist. When the limit doesn't exist, we have a jump discontinuity, because here it is going to 5 from the right, but it's going to 4 from the left, and we have a jump discontinuity. Describe the end behavior. We can just check x values far to the left, far to the right. Let's just call that f of x, then I won't have to change that. So let's go to the left, and let's go to the right. And then we just put these x values into that function, and we look to see what the y value is approaching to the left and to the right. So pause the video, fill out the table, and then describe the end behavior as limits. So with a calculator we get this. And we see to the right the y values are going to infinity. To the left they're going to infinity. So we write the limit as x goes to negative infinity is infinity. This means left. So we're talking about the left here. That means the left. We're talking about left here. This means left. That's why we have negative infinity. This is the y value, and that's what we put there. The limit as x goes to the right is positive infinity. All right, graphing. So if we look at the parent function, we know the parent function has these points. Absolute y is the absolute value of x. The absolute value of negative 1 is 1. So we get these points. So we can say we have negative 1, 1, 0, 0, and 1, 1. Let's do the reflection first. Every time we multiply or divide, we'll do that first. So negative is on the outside. That means it's changing the y values. And let's just multiply all the y values by negative 1. The x values didn't change. Now we'll do the translations. And we're going to add 1 to the x values and add 2 to the y values. Add 1 to the x, add 1 to the x, add 2 to the y, and graph. So we have the parent function look like that. And now this, the transformation is 0, 1, 1, 2, sorry, 1, 2, that's not there, and 2, 1. So here let's look at the parent function being that, and we can find, let's use 0, 1, and 4. The square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, so we have these 3 points for the parent function. And we have multiplication. We're going to multiply the y, and we're going to subtract 1 from the x. So that's an inside. That means it's changing the x. That's outside. That means it's changing the y. We can do them at the same time because we're changing different coordinates. Let's multiply the y by 2. times 2 times 2 times 2. Subtract 1 from the x. Subtract 1, subtract 1. The parent function, and then we go negative 1, 0, 0, 2, and 1, 2, 3, 4. All right, f of g. Let's copy f and leave a space where the x is. Copy f, leave a space, and in the space we put g. We can combine those, but we can't do things like, we can't do this. Some people were doing this. Cross out that and cross out that. They cancel, and then they would say maybe it's 2x plus 1. That can't happen. We can't do that because of these plus signs. You can't cancel one thing and not cancel the other. We also can't do things like this, even if they were squares. This is not this. So we can't square root the terms. So make sure you know that that's not how to do it. Let's do g of f. Pause the video and try g of f. Copy g, leaving space. And in the spaces, you put f. So now we can apply that. We can cancel that. X minus 1. This won't be on the test, to remember to do that. But when we square the radical, we would say that everything we get here needs to be positive. By doing a square root and squaring, we know this value that we get in here will always be positive. But if I didn't put the absolute value, it would be possible to get a negative in there. Okay. Is f of x 1 to 1? If it is 1 to 1, find the inverse function. So let's look at the graph. We know that the parent function for a radical looks like that, and this moves it to the right. So the graph is like that. It passes the horizontal line test. Every horizontal line will only touch it at most once. So passes horizontal line test, and f of x is 1 to 1. That means when we find its inverse, the inverse will be a function. So to find the inverse, here's the function, here's the inverse by switching the x and the y. And now let's isolate y. So we say the inverse function is x squared plus 2. But we have to restrict it because over here the domain of this is 2 to infinity. You can put a 2 there, but you can't put a 1. 1 minus 2 is negative, so that's not in the domain of this. Here the domain of the graph starts at 2 and goes to infinity. So we would say the domain is there, the range is 0 to infinity, because all the y values starting at 0 going to infinity have points on the graph. Then, to find the domain of this, we use the range of this. The domain is 0 to infinity, and it just says restrict the domain, so we have this function, but with this domain. We restricted the domain. All right, let's find f divided by g and its domain. Let's think about the domain of f and the domain of g. All right. Here, it's a radical that got shifted to the right, so we know the domain of this starts at 1 and goes to infinity. There's the domain. Every polynomial has all real numbers, so it goes in both directions for g, for the domain. But now let's write f divided by g, f divided by g. Okay, so we have to have the domain. I can't choose numbers over here, even though they do work in the denominator. They're in the domain of the denominator, but these numbers would not be in the domain of the numerator. So we want to look at these two domains and combine them. So we're going to go from 1 to infinity, but we also have to be careful. Will the denominator ever equal 0? So we would check x squared plus x plus 2. Does it ever equal 0? Well, we can't factor, so let's do the quadratic formula. X equals negative b, negative 1, b squared minus 4ac over 2a. 1 minus 8. So this tells us that, just by looking at the inside of the radical, that there are no real numbers that make this equal to 0. That means this will never be 0, and we don't have to further restrict the domain of this. So the domain is just going to be 1 to infinity, and we can include 1. And you try g divided by f. Pause the video and try that one. So now we have g divided by f. We already know there's no problem with this. This has all real numbers for the domain. This has a domain of 1 to infinity. But we have to be careful because even though 1 is okay to put in the radical, now we can't put a 1 there because it's in the denominator. So instead of 1 to infinity, let's instead of 1 to infinity, including 1, now we have to exclude 1, and that's another restriction. Last problem. Okay, we just have to graph these points, and then we switch the x and the y to graph the inverse. -3, 0, -3, 0, -2, 2, 0, 3, 2, 3. So we have that graph, and then we just switch all of these, so we'll have 0, -3, 2, -2, 3, 0, 3, 2. For the inverse, now we go 0, -3, over 0, down 3, over 2, down 2, over 3, down 0, and then over 3, up 2, over 3, up 2. And we see the symmetry to the line y equals x. So if you don't see that symmetry, then there was a mistake in graphing the inverse or in graphing the function, but that's all we have to do there. And that is the end.